Topic on solubility. Let's discuss some terms. Solvent is the chemical that will do the dissolving. Often the solvent is water. Solute is the chemical that dissolves into the solvent. The solute may be a solid like salt, in which case you get salty water, but it may be a gas like hydrogen chloride gas, in which case you get hydrochloric acid. Doesn't have to be a solid. Whatever dissolves is the solute. Together, when the solute and the solvent they make a solution. In the solution, the solute breaks up into the particles that make it up. So if ions make it up, then the ions break off into the water or some other solvent. If molecules make it up, then the molecules will break off and start moving around amongst the water, etc. That's what dissolving is about, and this topic deals with that. The quantity of dissolved chemical, the quantity of solute dissolved, is quantified in terms of numbers and values by measuring the amount of it, usually in grams, but then we need to stipulate how much of the solvent should we take. Obviously, if you take a swimming pool load, you'll get more salt to dissolve in a swimming pool than you will if you had a cup of water. The industry standard, the agreed scientific standard that everyone's agreed, is that let's agree that we're going to use 100 grams of water. 100 grams of water is not too small and it's not too big. 100 grams of water is like a small cupful. How much salt dissolved in a small cupful, if you measure it, it'll be about 35 grams, and therefore the solubility is 35 grams of salt per 100 grams of water. It's always per 100 grams of water. You have to scale up or down to quote to people who are reading your science. You've got to quote using the industry standard of 100 grams of solvent or 100 grams of water, because most of the time the solvent is water. And you measure how much solvent. That's wrong. That word there of solvent is wrong. That word should be solute. We measure how much solute will dissolve in 100 grams. Sorry, that's my stick falling on the floor. Okay, let's carry on. So, important points which you've got to know. The units of dissolving are how many grams dissolve per 100 grams of water. The quantity of the dissolved stuff, the quantity of solutes that will dissolve in a given 100 centimetre cubes of water will depend on the temperature. So if you give a value like 10 grams dissolves in 100 grams of water, you must say what temperature you're talking about. Solubility is linked to temperature. And if you plot solubility against temperature on a graph paper, then the line graph is called a solubility curve. Potassium nitrate is very, very soluble. Nitrates generally are very, very soluble. Sodium chloride is household salt. You know it's soluble, but it's not very, very soluble. It's just soluble. Let's have a look at their solubility curves. This blue curve is potassium nitrate. See, at normal temperature, say room temperature is about here, then more potassium nitrate will dissolve and less sodium chloride will dissolve. At really cold temperatures, say you got cold water at 2 degrees, then more salt will dissolve and less potassium nitrate will dissolve. Very, very high temperatures, say 90 degrees. A lot more potassium nitrate will dissolve at 90 degrees then sodium chloride will dissolve at 90 degrees. These curves, solubility curves, they tell you how the solubility changes as the temperature changes. As the water gets warmer and warmer and warmer, how does the solubility in grams per 100 grams of water, how that changes? And most of the time, with solids, most of the time, as the water becomes hotter and the temperature increases, then more and more solute will dissolve. More solid will dissolve. So if you want a lot of solid to dissolve, you use hotter water. Now, saturated solution, what's that? Firstly, you came across the term saturated when you did organic chemistry and you had double bonds. I want to say that this word saturated in this topic is not to be confused with the word saturated in that topic. The word saturated here means at a given temperature. If you've got a given temperature and you're dissolving things, then eventually you come to a point at which when you put more and more and more solute in to your solvent, you're dissolving it, you put more and more and more in, eventually no more solute will dissolve. No more will dissolve at that temperature. That means that the maximum amount that's going to dissolve has dissolved, and the extra after that will just float around or sink or hang around, or in the mixture it will not dissolve. I want you to learn this. The word saturated, when at a given temperature the solution, that's the mixture, holds as much solute, that's the dissolved stuff, as possible, and no more solute dissolves, then that solution is saturated. So the word saturated means when the solution can dissolve no more solute at that temperature, then that solution is saturated. Solubility curves separate where the solution is saturated from where the solution is not saturated. So let's go back. Solubility. Say we had a solubility here, like, say we had that quantity. Let's pick that quantity there. Say that quantity was like 70 grams. 70 grams of potassium nitrate dissolves at that temperature. Then if you make the temperature more, you get more and more than 70 to dissolve. Say you've got a temperature here. Say you've got a hot solution and you cool it down. Eventually that hot solution will hit, the solubility in there will hit this line at that temperature, and then you get crystals. The extra solute that is present will come out as crystals, and those crystals will form. You'll see them. If you cool it down more and more and more, you get more and more crystals, more and more and more crystals. So what I'm trying to say is, when the dissolved things are there, they're inside the solution. If you cool it down and the solubility gets less and less, there's a chance that crystals are going to come out of solution, and they will come out as crystals. And those crystals coming out, believe it or not, the process is called crystallization. So you see the crystallization if you cool solutions down. I will come back to this point and you will see it in practicals, and I'll try and demonstrate it to you as well. But crystallization is a function of you exceeding the solubility. If you exceed the solubility, the extra solid dissolved will come out as crystals. And that's the fundamental theory behind crystallization. My thing is slipping down. If we put in more solute that will dissolve, the extra solute will exist as a solid coming out as crystals, which is what I've just been talking about. Now, this is what I was trying to do to you earlier. I was trying to talk about it without this kind of detailed diagram, but now I've got a detailed diagram. I want you to think, say you've got a solubility curve, this is the solubility curve, and you've got a solution here, X, and you're cooling it down, and say you cool it down, that's 60, that's 80, halfway is 70, so I would say that there is about 76. Imagine 25 grams is dissolved. So 25 grams of dissolved solute is dissolved, and when it comes here, that 25 grams, that much will stay dissolved. But then when you cool it down, the solubility gets less. Then the extra solid comes out as crystals. Say we cool something from 76 degrees, say we cool it down to 20 degrees. And 20 degrees, that point is 9 grams. Solubility in grams per 100 grams of water. Say that's 9 grams. 25 grams was dissolved. At 20 degrees, only 9 grams can dissolve. So how many crystals have or must come out of solution in this crystallization? You must get the difference between 25 take away 9, 25 take away 9 is 16 grams of crystals will form, and that 16 grams of crystals will be per 100 grams of water or solution that you've got. So 16 grams of crystals will form per 100 centimetre cubes of water that you've used to make your solution in the first place. These kind of calculations can get tricky. All you've got to remember is you're dealing with a solubility curve that is per 100 grams. If in the question you've only got 50 grams, then you've got to half your calculations. Or say in the question you're given 200 grams, well then you've got to double your calculation, etc. So the solubility curve is always per 100 grams of water, and you have to use your common sense to scale up or down as appropriate. Remember, the units are per 100 grams of solvent. Some things, some solutes dissolve very well. I want you to remember that nitrates dissolve really well. Any nitrate dissolves really well. I want you to remember that any sodium, potassium or ammonium thing dissolves really well. So sodium, potassium, ammonium things and nitrate things all dissolve really, really well. Now, these are rules. These are rules that we've got to teach you, and later I'm going to give you a solubility table to learn, and you need these kind of rules in this topic. So some things have a really good solubility. Some things have a very bad solubility. So the numbers are low, only a little bit dissolves. And some things do not dissolve. Now, let's talk about that a little bit more detail. Why would something not dissolve? Well, sometimes the attractions are so strong that the water can't separate the particles that you're trying to dissolve. So say you throw aluminium oxide. If you put aluminium oxide into water, it doesn't dissolve because the aluminium ion is 3+, the oxide ion is 2-. Strong attraction, so strong the water can't break that apart, and aluminium oxide therefore does not dissolve. If the attractions are very strong, like aluminium oxide, then things will not dissolve at all. But most things will dissolve to some extent, and some things will dissolve very easily. And solids, the solubility tends to increase with temperature. However, with gases, it's the opposite. Gases tend to dissolve better at colder temperature water. So colder temperature water will dissolve more gas than hotter temperature water. It's the opposite of what solids do. Here I've got some solubility curves that are to do with gases. More gas will dissolve in colder water. See, temperature, when the temperature is colder, the solubility is more and more and more. And the curves go down as the water gets hotter and hotter and hotter. There is a thing called a fountain experiment. Now, the fountain experiment is something that I've demonstrated. I will demonstrate on the next video, and I'll upload it so you can see this. And very famous experiment because it only works with very soluble gases, and the gas we do it with is ammonia. Like ammonia is your famous example of a weak alkali. So you put your water and indicator in here, and we put universal indicator. So water, universal indicator, you might think that the indicator is green. In fact, when I do it, I put a few drops of acid. In there, and it's red. So down here is red. And what happens is you blow to push a little bit of this up into the top flask is full of ammonia. Now ammonia is an alkaline gas. This water, when it goes up as a fountain, will dissolve the gas into itself. As the water dissolves the gas, it causes suction. When that water dissolving, suction sucks the water up. You get a fountain effect, which is quite spectacular. And the indicator up there will be blue because ammonia is an alkaline gas. So if you watch the next video, I do that. Sorry, my phone is slipping off my tripod. So basically, the solubility of gases is different to the solubility of solids. Let's have a look to see what happens when things are dissolving. I want you to know that the particles of a solid in water, when the solid dissolves, they break up. The individual particles separate and they start moving around amongst the water particles. So this is supposed to be sodium chloride. The water, which is these things, that's water. The water, if you like, pulls. It pulls the chloride ions and it pulls the sodium ions off. It pulls them off from that structure and separates them. And as they separate, then that lump of sodium chloride gets smaller and smaller and smaller and smaller. When all the ions have all separated into individual ions moving around amongst the water, they're so small that they cannot then be seen. You can't look at a solution and see these individual particles. You can only look at a solution and see big lumps and crystals that might exist, because you need millions of ions together for your eye to be able to see them. Your eye will never see individual ions. So solutions always look transparent, and where something doesn't dissolve, then those mixtures look opaque. Another diagram about how it happens, say you've got solid, salty water, sodium chloride. That's when you throw salt into water, you get bits of salt floating around. But then as the individual ions separate, they separate into individual ions, and then the individual ions are no longer visible by the naked eye, and the salty water looks colourless. I've got lots of solubility curves. You can see potassium nitrate has a really good solubility, whereas sodium chloride does not have that change in solubility like potassium nitrate does. And all the different solutes, all the different solids have their own solubility, which you have to do experiments to work out. And my next video will show how we might do a solubility curve for ammonium chloride. Now, ammonium chloride is a very soluble solid. It's not one that's on that list, I'm afraid. But watch my next video and we'll explain how it's done. You have to be able to interpret solubility curves. You've got to be able to do calculations that involve quantities or moles calculations when it comes to it. Do not confuse the two saturated terms. So in red, I've got those two saturated terms I want you to learn. A saturated solution, that's this topic, is one which can hold no more dissolved solutes at a given temperature. Normally there are 2 marks for that, so get it right. Whereas a saturated molecule is a molecule where all the bonds, the covalent bonds, are single ones. Now that is more to do with organic chemistry, and we've done that when it came to organic chemistry. Now this is the solubility table I want you to learn. So learn this solubility table parrot fashion. Now parrot fashion means memorize it, learn it, memorize it. Sodium, potassium, ammonium and nitrate, they all dissolve. They are soluble. Most carbonates are not soluble, except obviously the sodium, potassium, ammonium varieties. Most hydroxides are not soluble, except sodium, potassium hydroxide are soluble, and calcium hydroxide is slightly soluble. The reason you need to know calcium hydroxide is slightly soluble is that is lime water. Calcium hydroxide dissolved in water, a little bit dissolves, that's lime water. Most sulfates dissolve except lead sulfate, barium sulfate, they don't dissolve. Most chlorides, bromides, iodides dissolve or soluble except silver and lead chlorides, bromides and iodides, they don't dissolve. This solubility table will be invaluable in this topic. You cannot do making salts without learning that table. So learn it parrot fashion. Okay, we'll stop there.